Welcome to another episode of my reviewer series for civil engineering topics focusing on fluid mechanics problems. In this episode, the pipe connection shown consists of series and parallel connections. The rate of flow in pipeline 1 is 300 liters per second. Assuming equal values of F equals 0.02 for all pipes, we are to determine the discharges at pipeline 2, pipeline 3, and pipeline 4. Shown on the table below are the data for the specifications of each pipeline. Before we proceed with our solution, refresh muna tayo sa mga concepts na gagamitin natin for this problem. Given the condition na series and parallel connections ang meron sa pipeline system natin, we should be aware that some parts of it have equal discharges and some do not. Para sa series, ang bawat pipes na included sa system na to are undergoing an equal rate of flow. So yung daloy from point A to point C is consistent lang dapat yung discharge. For the head loss naman, or yung pagbawas ng energy or pressure ng fluid as it flows through the pipelines, we have to consider na dahil magkakaiba yung specifications ng tube, mag-iiba-iba rin yung magnitude ng head loss sa bawat pipe na dadaanan ng fluid natin. Thus, for the total head loss from A to C, we can express this as the sum of all head losses. About the parallel connection system naman, when a pipe is branched out, kagaya na lang ng pinapakita dito sa figure, na from pipe A, nahati siya into pipe B and C, the rate of flow is also relatively divided to those branches, given that it also reconnects at one point. But supposedly when summed up, dapat equal pa rin yung total nila dun sa initial flow discharge na pinanggalingan. That's why we can express the value of flow rates in the given system as discharge at A equal to the sum of discharge at B and discharge at C. And since sa bandang dulo nag-meet lang ulit yung dalawang branch out na connections, we can say that the sum of the two discharges from B and C is also equal to the discharge of pipeline D. Other than that, parallel pipes and systems that are within the branched out connections should have an equal head loss value if those branched out pipes or systems are reconnected at the end into a singular pipeline. Basing the idea on this figure, pipe B and pipe C yung merong equal head loss values. Now that we have recalled these conditions, we just have to apply this to our problem para ma-determine natin yung mga unknown discharges. So stating the boundary conditions of our figure muna, or kung alin lang yung merong specific application ng series and parallel connection conditions natin, i-express natin lahat ng possible relationships ng pipes for the convenience ng pagsusolve later on. Starting with the parallel pipelines, we can observe that number 3 and number 4 are in series connection. Therefore, we can say that their discharge are of equal value. Given that idea, it is also applicable if we consider these two pipes as one na lang when solving for the discharge only. Pagdating kasi sa head loss as stated kanina, totaled ang value when in series yung connection. So separately kinoconsider ang values nila and differently din if magkakaiba naman yung specifications ng pipes. Moving forward, yung pipeline 2 and pipeline 3 to 4 is in parallel arrangement, branching out from pipeline 1 and reconnecting at pipeline 5. Therefore, we can express this as either discharge Q1 equal to Q2 plus Q3 or Q1 equal to Q2 plus Q4. And since sa dulo magme-merge lang sila into pipeline 5, we can also say that Q5 is also just equal to Q1. Additionally, it was stated sa given situation na ang value ng Q1 natin is equal to 300 liters per second. So consider din natin yan sa expressions natin. Lastly, in terms of head loss naman, since meron tayong series connection na parallel sa pipeline 2, we can express this as the head loss of 2 equal to the head loss from both pipeline 3 and 4. Now that we have considered all possible boundary conditions, move on naman tayo sa formulas na gagamitin natin. Since discharge or rate of flow ang usapan, syempre di mawawala yung general formula natin na Q equals AV, where Q is the rate of flow, A is the wetted cross-section area, and v is the velocity of the flow. Furthermore, ang head loss natin is observed within channel conditions. Therefore, gamit tayo ng isa sa mga channel flow equations. Pero kung mapapansin nyo, di naman specified sa problem natin kung anong specific equation ang gagamitin natin. So, let's take a look muna kung ano yung present parameters natin and kung aling equation ang pwede natin gamitin for that. Recalling our possible formulas such as Manning, Darcy-Weisbach, and Hazel-Williams equation, the variables that make each other distinctive is yung mga indicated na coefficient factors as shown in the table. And seeing na yung given natin sa problem is stated as F, or also known as a friction factor, ang gagamitin nating formula for the head loss is from Darcy-Weisbach. And according to this formula, the head loss of a channel is equal to FLV squared over 2dg, wherein yung L natin is yung length ng channel or ng pipe, V is the velocity of the flow, D is the diameter of the pipe, and G is the acceleration due to gravity. So take note lang, itong formula na to is specifically for circular pipes lang, given na isa sa mga variables ng equation is diameter of a circle. Derived lang to from a general formula para mas mapabilis yung pag-solve natin. Pero going back, let's get started na sa pag-perform ng solution. And para convenient, solve muna natin yung area values ng bawat pipe. Given naman na lahat sila ay may circular cross-section, sundan lang natin yung formula na pi over 4 times diameter squared. Then, list na rin natin alongside ng table natin yung masasolve nating area for each pipeline. Next naman, ang pipelines in question natin are pipes 2, 3, and 4. And if we are to look at our unknowns given these pipelines, hindi lang discharge ang undetermined sa kanila, kundi pati na rin yung mga head loss kung i-utilize natin yung mga channel slope equations. So in total, there are actually 6 unknown variables that we need to solve for. Given that, kailangan makapag-derive din tayo ng 6 na equation para makuha lahat ng mga values na yun. Pero no worries masyado sa part na to. Kasi yung first 3 equations natin is actually pwede na natin makuha from our boundary conditions. And the other 3 naman, pwede natin makuha by using the channel flow or head loss equation for each of the pipelines. So using the equation according to Darcy-Weisbach, plug in muna natin yung mga values na meron tayo. Starting with the head loss at pipeline 2, which we denote as H2, the value of F as given is 0.02. And looking at the values na given sa table, the length L of the pipe is equal to 150 meters. Then for the velocity, since di given yung value niya and ayaw naman na natin madagdagan pa yung mga unknown variables natin, express na lang natin to in terms of a general formula na Q equals VA. So modifying that equation, V is equal to Q over A. And since meron tayong area value na given na rin sa table, plug na rin natin to sa equation, same with the diameter na indicated rin. Lastly, G value natin is just the standard na 9.81 meter per second squared. Simplifying the equation formed, our H2 is just equal to 724.392 Q2 squared. Tapos kung ano yung ginawa natin dito sa head loss ng pipeline 2, apply lang rin natin siya sa pipelines 3 and 4. So for head loss at pipeline 3, we will get an expression of 362.196 Q3 squared. And for pipeline 4 naman, this is equal to 61.752 Q4 squared. With that, kumpleto na yung 6 equations natin for our 6 unknowns. The only thing that we need to do is to utilize these equations in such a way that we can cancel out other values and retain at least one muna. So for this case, ganito lang gagawin natin. Kung mapapansin nyo, since ang present head loss lang na ino-observe natin is from the pipelines 2, 3, and 4, pwede natin gamitin yung mga head loss equations sa isa sa mga boundary conditions natin, which is yung H2 equals H3 plus H4. Plugging in those expressions, we will get 724.39 Q2 squared equal to 362.196 Q3 squared plus 61.752 Q4 squared. Tapos, since indicated din sa boundary conditions natin na ang Q3 is also equal to Q4, pwede natin gawing same values na lang to sa nasulat nating equation. So for this case, gawin na lang natin to both Q3. And given this, pwede natin ipag-combine yung values with similar terms, and simplifying the equation, we will have Q3 squared equal to 1.7087 Q2 squared. Applying square root on both sides, Q3 equal to 1.307 Q2 na lang yung expression. Up next, from our boundary conditions, i-utilize na natin yung equation na Q2 plus Q3 equal to 300 liters per second. So technically at this point, we are down to two equations for two unknowns na. Pero keep in mind nga pala, ang unit of measurement na ginagamit natin in terms of volume is cubic meters. Therefore, need muna natin i-convert si 300 liters per second. So 1 cubic meter is equal to 1,000 liters. Therefore, 300 liters is just equal to 0.3 cubic meters. Using Q3 equal to 1.307 Q2 para sa equation na to, we can write this as Q2 plus 1.307 Q2 equal to 0.3. And further simplifying, finally, we will get the value of our pipeline to discharge, which is equal to 0.13 cubic meters per second. At this point, mabilis na natin makukuha yung ibang discharge. Kasi kung ipa-plug lang natin yung value nito sa Q3 equal to 1.307 Q2 squared, we will get a value of 0.17 cubic meters per second for the discharge of pipeline 3. And since as stated sa boundary conditions natin, Q3 is just equal to Q4. Therefore, we don't really have to solve for anything anymore since Q4 is also just equal to 0.17. And that's it. For further questions, feel free to type it in the comments below. And with that, this situation is finally solved.